The moon is a relatively close celestial object, so its distance can be measured directly by taking two different photographs at precisely the same time from two different locations. The moon will have a different angle of elevation at each location. Okay, so on April 29th, 1976 at 11:35 a.m., the lunar angles of elevation during a partial solar eclipse at Bochum in Upper Germany and at Donaueschingen in Lower Germany were measured as 52.6997 degrees and 52.7430 degrees, respectively. The two cities are 398 kilometers apart. Calculate the distance to the moon to the nearest 1,000 kilometers from Bochum on this day and compare it with the actual value of 406,000 kilometers. Disregard the curvature of Earth in this calculation. Okay, so we're going to need to solve a triangle here. That's the idea. And there's so much value in being able to solve triangles because this comes up in so many situations in chemistry, biology, engineering, etc. But not just right triangles, any triangle. And with our knowledge of solving triangles, right triangles using trigonometry, just trigonometric functions, combined with what we're learning now with the law of sines and cosines, we can solve any triangle, assuming we have enough information to start with. So, okay, what we're wanting to solve for is this distance from Bochum to the moon. Okay, so what we have is, what the information we have, we know that the two cities are 398 kilometers apart. We're going to neglect the curvature of the Earth, which seems like a good assumption. So this is 398 kilometers, this side length. Now, when it comes to triangles, it's good to use the labeling convention. So you pick whatever vertices you want to be A, B, and C. You know, that's just whatever you want. But then from there, the side length opposite of angle A is lowercase a. The side length opposite of angle B is lowercase b. And the side length opposite of angle C is lowercase c. So lowercase c is 398 kilometers. Okay. Now, let's see. So what other information do we have? The lunar angles of elevation from Bochum and Donaueschingen were measured as shown here. So what they're referring to is this is the angle of elevation from Bochum. So we can see that's going to be angle A. So it tells us that angle A is 52.6997 degrees. Okay. But then this other angle is here's the angle of elevation. Angles of elevation are from the horizontal, the ground level. So that's what they're referring to. But if we can get angle B from that, because we can see that this angle is supplementary to angle B. So we can take 180 minus 52.7430, 127.257 is angle B. Okay, now we might not need it, but we can easily get angle C now because we know that the sum of the angles of a triangle sum to 180. So add that to, all right, now subtract that 180, and that's going to be angle C. So yeah, that's why they're saying this is not to scale. It's just drawn this way for illustration. This is a really small angle, which makes sense because the distance from Bochum to however you pronounce this is going to be small relative to the actual distance to the moon, which would mean that this angle is small. So 0.0433 degrees. We're trying to carry as much of the numbers as possible, the digits. Okay. So now let's apply what we're trying to solve for is B, side B here. So we can apply the law of sines. So the sine of, well, let's put the side lengths on in the numerator, make it a little bit easier. It doesn't really matter. So, okay, side length B over the sine of 127.257 is equal to, now we can pick any other pair. Let's do well, we only have side length, we have to use side length C. So, okay, side length C is 398 over the sine of 0.0433 degrees. So, okay, we can see that what we want to do is take 398, and what I'll try and do is to get this as accurate as possible, 398 times the sine of, and let me pick this angle straight from here, 127.257, and it carries all of the possible digits. I thought it was going to be more digits, but there might be even hidden digits here, and so if you select it straight from the calculator, it'll carry all of those digits. There's 398 times that, and then we're going to divide that by the sine of this 0.0433. And that's going to be in kilometers. So 419,171 kilometers. Oh, well, wait. No, they wanted it rounded to what? The nearest 1,000 kilometers. So round to the 1,000th place. So 419,000. Okay, now compare this to the actual value of 406,000. So I guess they measure the actual value from like the equator, some spot on the equator, maybe. And yeah, it's pretty close. The actual value being 406,000.